In this video, we are going to discuss families of functions. The reason families of functions are important is that they can share characteristics, just like a regular family can share characteristics such as eye color and hair. Function families will share attributes as well. Some of the attributes that you can see when you're talking about families of functions are the name. Sometimes the family will have names, the degree of the function, domain and range, x-intercept, y-intercept, and behavior. You can also have shared symmetry, and it just depends on what the family is. So let's look at the first family of functions. We're going to look at what we call a constant function. So a constant function has the form f of x is equal to a. Same as y is equal to a. This is going to be a, sorry, I had some stuff left over from before. This is going to be a horizontal line. It's a horizontal line at the value here of 0, a. Let's get rid of this other stuff. So when we look at f of x is equal to a, the name of the function is going to be constant. This has a degree that's equal to 0. Imagine that you've got an x to the 0 power here. Remember that x to the 0 power is equal to 1. So it doesn't need to be there, 1 times a, but that's where we get the degree equal to 0. My domain, you can see that we can plug in any x. The function's going to return a. So my domain is x is a member of the set of all real numbers. My range, the only possible y value that it's going to return is going to be a. My x-intercept, unless your a is equal to 0, we're going to have no x-intercepts. Let's make that little note here, unless a is equal to 0. If a is equal to 0, what you're talking about is the x-axis, and you're going to have an infinite number of x-intercepts. The y-intercept is at 0a. We've already discussed that. And the end behavior, check out the notation. As x approaches positive infinity, y is going to be equal to a. As x approaches negative infinity, y is equal to a. No matter how far we go out on the x-axis, what's going to be returned is y is equal to a. All right, let's go on to the next function. My next function is linear. So f of x is equal to x. This name is, as we've said, linear. The degree, again, this one has something invisible as well. This is really x to the first power, so my degree is going to be equal to 1. The graph of y is equal to x is the diagonal line here. So it goes through the x and y. It goes through the origin. And my domain, like most linear functions, like all linear functions, x is going to be a member of all real numbers. Range, you can check out the y. Every single y is going to be covered as well, so y is a member of all real numbers. For the parent function here, my x-intercept is going to be 0, 0. My y-intercept is going to be the same. Now the end behavior here, you can see as we go out towards positive infinity, my y is going to keep going up and up and up and up and up. So as x approaches positive infinity, y is going to approach positive infinity. As we go the other direction, as we go towards negative infinity, you notice your y value is going down. So that means as x approaches negative infinity, y is also going to approach negative infinity. Oops. Let's get rid of that. y is going to approach positive infinity. And those are your linear, that's your linear family. Next one is quadratic. So what we have here is called a quadratic function. That's an A. The degree, we can see the power is 2. That makes the degree equal to 2. Remember that what we get here is a parabola. So with the parent function, we get the vertex at 0, 0, and we're going up. My domain, x is going to be a member of all real numbers. And we don't get any points down here. 0, 0 is the minimum. So my range is going to be y is greater than or equal to 0. X-intercept, again, my vertex for y is equal to x squared is 0, 0. That's going to make my y-intercept the same. End behavior, as x approaches positive infinity, oops, let's just make that positive infinity, y is going to approach positive infinity. As x approaches negative infinity, y is going to approach positive infinity. As you go out on the x-axis this direction, your y is going up. As you go towards the negative infinity, your y is going up. And those are your quadratics. Next function is a cubic. So for a cubic function, its name is cubic. Degree we can see is 3. Cubic function looks kind of like this. My domain is x is a member of all real numbers. Think about it, you can plug anything into that x. My range, same thing. My range is going to be a member of all real numbers. X-intercept is at 0, 0. Y-intercept, 0, 0. End behavior, as x approaches positive infinity, y is going to approach positive infinity. As x approaches negative infinity, y approaches negative infinity. Again, going out on the x, you can see that the y is going up. As we go towards negative infinity, my y is going down. Now, we're not going to go through all of them, but even-powered functions like x to the 4th, x squared, x to the 6th, are also going to share some similarities. Some of the similarities that you're going to see are like your symmetry, Okay, so the name, you're really not going to hear the names very often. To the 4th power is called a quartic, but honestly, except for teaching, I've never heard that. We just call it to the 4th degree. It's a polynomial of the 4th degree. So in this case, it's going to be 4, 6, 8, etc. Even 2s. And they're going to share a lot of the characteristics. It's going to go down like a parabola and back up. Now, depending on the transformation, funky things can happen in here, but this is why end behavior is important, because the end behavior is always going to be the same. So just like the quadratics, as x approaches positive infinity, y approaches positive infinity. I don't know why I keep doing that. As x approaches negative infinity, my y is going to approach positive infinity. My domain, just like the quadratic, x is a member of the set of all real numbers, and my range y is going to be greater than, let's try that again, y is going to be greater than or equal to 0. My x-intercept is going to be at 0, 0, and my y-intercept is going to be at 0, 0. Now, you already know about symmetry for even functions. You can see that we're symmetrical to the y-axis. We'll talk about symmetry some other time. Again, just like the even powers, odd powers are going to act similar to each other. So that would be a degree, 3, 5, 7, etc. And just like the cubic, it's going to start down here, go through the origin, and then go up. Now again, things in the middle here as you get closer to 0 might be a little bit different. They'll go up faster the higher the degree, but a lot of these are the same, like the domain. Again, x is a member of all real numbers, and y is going to be a member of all real numbers. Nothing needs to be excluded. My x-intercept is 0, 0. My y-intercept is 0, 0. My end behavior, as x approaches positive infinity, you can see that we're going up, so y approaches positive infinity. As x approaches negative infinity, so we're going out towards the left, y is going to approach negative infinity. And that's it for the polynomial functions. So let's talk about some of the other types. Let's look at square roots. So square roots account for the ones with the invisible 2. You've got other roots in there, even roots, odd roots. They are the inverse of the polynomial functions. We'll look at those more specifically when we talk about inverses. So the degree, it's not a polynomial, so it's not going to have a degree of this function. You can look at the power. This is actually x to the 1/2, so you can look at it that way. This graph is going to look like this. It's going to look like half of a parabola on its side. Now, x is going to be greater than or equal to 0 for an even root. You cannot have a negative if you're talking about the real world with real numbers. If you've got a negative value in there, you're going to get into complex numbers. My range, since we don't have any negatives in there, the square root of any positive number is going to be positive, so y is greater than or equal to 0. My x-intercept is 0, 0. My y-intercept is 0, 0. As x approaches positive infinity, y is going to approach positive infinity. As we go out in this direction, my y value is going to go up. We don't have to worry about the other side because we don't evaluate the negatives because they're not in our domain. Next, we have exponential functions. Exponential functions where this number a is a constant. So that would be like 2 to the x. If you remember, we're going to look like this going up. This one we call an exponential function. Again, degree doesn't make any sense. Our degree is the x. My domain, we don't have to exclude anything. X is going to be a member of all real numbers. Now, 2 to any power is going to get closer and closer and closer to 0, but it's never going to reach it. So my range is going to be y is greater than 0. My x-intercept, if we can't get to 0, we can't cross the x-intercept, so we're going to have none. My y-intercept, think about it, if x is equal to 0, a to the 0 power is going to be equal to 1. So we're going to have a y-intercept at 0, 1. My end behavior as x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y is going to get closer and closer and closer to 0. Let's go. We'll talk about what this means and what happens as we go this direction and we approach 0 at another time. It's called an asymptote, and we'll talk about that later. Next function we have is called the rational functions. Rational functions have a parent function of 1 over x. This is going to give you a function like this, where now we have two asymptotes, whereas we had an asymptote at y equals 0 previously for the last function, for the exponential function. We're going to have both an x and a y asymptote. So these are called rational functions. Again, degree doesn't make much sense. Domain. Now, we can't divide by 0, so we have to exclude that. So my domain is going to be the set of all x such that x cannot be equal to 0. My range, my y here, we're never going to get to y is equal to 0. So my range is going to be the same, y, such that y cannot be equal to 0. If I have no, if x can't be 0 and y can't be 0, we're going to have no x or y intercepts. Now, in behavior here, you can see because of the asymptote, remember we have an asymptote at y equals 0, my end behavior as x approaches positive infinity, as x approaches negative infinity, my y is going to approach 0 from opposite sides. As x approaches positive infinity here, you can see that the y approaches 0 from the positive side, either the first or second quadrant. As x approaches negative infinity, y is going to be equal to 0 again, but it's approaching it from the negative side, the third and fourth quadrants. And there are other functions, and we'll talk about them as they come up. We can, we'll have logarithmic functions, which is the opposite or inverse of the exponential functions. We have cube roots, fifth roots, fourth roots, different types of root functions. We have the trig functions. We'll have sine, cosine, tangent, secant, cosecant, and cotangent as well, but we will talk about those and their attributes as they come up. Now, again, it's important to know the families of functions, because if we look at a parent function, now a parent function is going to be, sorry, let me find this slide. A parent function is going to be the simplest in a family of functions. So if we take y is equal to 2 times x minus 3 squared plus 1, if we take all of the numbers away, p of x is going to be equal to x squared. This here, no numbers, is the simplest in the quadratic family. And what's powerful about the parent function is that you can apply transformations to get to any other member in the family. So if you know the parent function, you know the attributes of the parent function, then you can analyze and graph um, all of the other functions in that family. And we will be talking about transformations next time.